Hello everyone, welcome back to our NDT training session. I am Mutlakmi Kanagaraj, quality expert, and it's great to continue our journey into the world of non-destructive testing. Now we are discussing about the inducing magnetic fields in test objects. Let's start our session. First, field variation and optimization. The magnetic field density inside a test object is not always uniform. It depends on the shape and size of the object. For irregular shaped objects like gears or crankshafts, the field may not fully cover all areas. To solve this, direct field indicators such as shims or Hall effect probes, these are used to measure flux density and confirm whether the applied current is adequate. In cases where the shape changes significantly, like automotive crankshafts with multiple diameters, a single magnetizing current won't be enough. Multiple current levels or shots are required to achieve full coverage and proper flaw detection. So these are the field variations and optimization. The next one is tubular objects. First, can be tested using a central conductor. A conductor is passed through the center of the tubular objects. That means hollow objects only used in central conductor methods. When current flows, it creates a circular magnetised field in the walls of the tubes. This is the tube and this is the central conductor. We pass the current through the conductor and here circular magnetic fields are created. This is very effective for detecting discontinuities on the inside and outside surfaces. Alternate method is wrap a coil through the object and rotate it. A coil wrapping method, a coil of wire is wrapped around or passed through the tube. This is the tube. Here wrap the coils like this. So current through the coil induces a longitudinal magnetic field along the length of the tube. So this is a longitudinal magnetic field. To ensure complete coverage, the tube may need to be rotated or tested in multiple setups since one orientation may not detect all flaws. So we can use multiple orientation to find all flaws or defects. The next topic is machined parts. Machined parts such as holes, slots, keyways or gear teeth create irregular magnetic paths. These changes in geometry can cause flux leakage. So it causes a flux leakage and make flaw detection more complex. So we are using the different magnetizing currents, that means AC, DC, half wave DC. It's depending on whether surface or subsurface flaws need to be detected, and vary the strength and direction of the magnetic field to cover all areas. Rotate the part and perform multiple magnetization shots if necessary. Example, a gear might need one circular field to check the teeth and another longitudinal field to check the root areas. So testing machined parts requires patience and planning. Testing machined part requires patience and planning. The one field direction is usually not enough. So multiple shots ensure all critical areas are inspected. The next one is deep holes and sharp gear teeth. So very deep holes, sharp corners or narrow gear teeth or areas where magnetic particles cannot easily settle. So flaws in these zones are hard to detect with conventional wet or dry particles. So we can use self-curing magnetic rubber containing suspended magnetic particles. Apply a high residual field or keep a continuous current flowing during the curing process. Once cured, peel the rubber from the part. It will carry the trapped magnetic particles with flaw indications clearly marked. For higher sensitivity, fluorescent particle can be used under UV light for visibility. So here magnetic rubber acts like a mold of the internal geometry, making invisible flaws visible, especially in areas normal particles cannot reach. This is a deep hole and sharp gear teeth. I hope you are all understanding this concept. So thank you. We will see the next video.